the fact that you're attending to SCED so we can help get a count. That would be really helpful for us. But we're looking forward to seeing everybody there. It should be a fun time. It's, of course, for registered connect, everybody who's registered to attend today. Tomorrow night there's a member services dinner, and again, you should have a calendar invite for that. So if you haven't yet received or responded, please let us know. If you're coming, say yes. If you can't make it, okay, but just at least tell us so that we can get a count. Should be a fun time. So if you haven't responded yet, please do so. And right here in this room tonight, there's a Linaro employee-only meeting. So if you're a Linaro employee, please be here 5 p.m. promptly. And so Wednesday's a special day at Connect. We started this, I'd say, 3 Connects ago or so, where there are no committee meetings. There are all sorts of committee meetings all week long, nonstop during the day, and there are all sorts of sessions. So Wednesday, sort of, we clear the schedule for something different. And so we have a few different things today, but it's also a hacking day for engineers. So the hacking rooms are usually pretty busy, or the hallways or whatnot, wherever you like to do some development work, that's fine. But we do have 3 interesting tracks today. One is kernel themed, so there's lots of kernel stuff going on. Lots of kernel sessions going on today. So if you're a kernel person, and I know we might have 1 or 2 in the room, you might find interest in that. Check the schedule. And also we're doing a security group focused task today, track today as well. So if you're interested in security, look at your schedule. You can see the sessions that are going on. There are so many kernel things going on today that it couldn't fit into a single track. So hopefully there's lots of interesting stuff for everybody. And it's sort of a break during the week to change the pattern. And then tomorrow on Thursday, we'll get back to our normal pattern for the week. Okay? Okay. And then we also have a whole bunch of students from UCSD who have joined us today. And there's a special track for them as well. And they have a private seminar. They have a hackathon with some prizes from Arrow and ShareTech. And so if you see them, welcome them to join us too. Is there anybody in the room today? If you're from UCSD, raise your hand. All right, very good. Welcome. We're really happy to have you here. Hope you have a great day. And so one of the things that, we're all technologists at heart, and we all spend most of our time working on technology. And one of the important things for most of us, I think, is how does technology affect our daily lives? And that's one of the themes that we'll see today in both keynotes, but especially the first keynote from Matsuoka-san, is about how does changes in technology, evolution in technology, change our daily life, ideally for the better, right? And we know it also raises challenges too. So the fact that we're here in San Diego makes it particularly interesting because San Diego is considered the smartest city in the country, if not one of the smartest cities in the world. And what do we mean by smart cities is they're using technology in many of the ways that we talk about it, and they're using it in the municipal infrastructure here, in the city infrastructure. And I'd like to share one example with you, but you can see just based on the tabs, this is the city. If you go to sandiego.gov, you'll see this. And they're using it for sustainability and energy and water efficiency and clean renewable energy and so on and so forth. So they're using technology in the best ways possible to help the city and to help the residents of the city and the visitors to the city. And this is so directly germane to what it is that we're doing, for example, in most of the segment groups in Linaro. It all the work that we're doing is, it all actually connects up to change people's lives for the better. And so there's a really good example of that in San Diego that I thought I would share. So there is this worldwide trend and thought and vision of this IoT technology and the proliferation of IoT, and to use that to improve city life. And San Diego is on the leading edge for doing that. San Diego has the world's largest network of IoT sensors on the city streetlights. And so basically, starting in 2014, they partnered with General Electric and then with Qualcomm and with AT&T to implement these smart streetlights. So they started out by installing 3,000 smart LED streetlights with wireless connectivity throughout the city. And just the LEDs and this wireless way of being able to power and manage them and control them saved the city $250,000 a year right off the bat. So a really good investment, right? Then they took it a step further, and they basically installed more intelligent streetlight lights. I thought about that word, streetlight lights. It's the first time I've ever seen it used, but it's actually correct. So now the lights are becoming even more intelligent, and they're capable of doing all sorts of interesting things for San Diego and the citizens here. right? They can monitor the parking spots. They can listen for criminal activity. They can check the air quality. They're capable of measuring and tracking the temperature, the barometric pressure, humidity. They can even count vehicles and count people. And one of the more interesting applications, if you start to look at this data, is they can actually report on illegally parked cars, right? So there's a revenue generation model in there somewhere too. But that's just a minor feature of the whole thing, right? And so there's all this information and all this data being collected, and it's being used in interesting ways. So for example, they're using the information to determine which intersections of the city are the most dangerous, and then the street department can basically look at the intersection and figure out, well, how can we redesign this to make it less dangerous? Right? So they're using the very technology that we develop and we work on in real ways to help people and save lives, if you will. They also look at the bicycle usage. Where are the streets that have the biggest bicycle usage, and what do the paths look like on that street, and where should we be improving our street infrastructure so that people who are riding bicycles can do so more safely, more quickly, and mix better with the traffic. And there's also something called the ShotSpotter network. And the ShotSpotter network is being able to detect when a gunshot goes off and alert the authorities when it picks up on a gunspot. So now they can use this technology in the streetlights to be able to detect if there's a gunshot somewhere in the city and react to it much more rapidly as a result of being able to pick up that information instantly and act on it. So those are just a few of the ideas of some of the usages. There's many others, but I thought those were some of the more interesting ones. So here's a map. They actually provide, if you go to the city government website, they actually provide an interactive real-time map where you can see all the smart streetlights that are in the city. And not only can you see them, but you can also interact with them as well. So as one example, I clicked on one of the streetlights. It tells you exactly the address of the streetlight. It tells you all sorts of information about it. It tells you even the type of light it is. It's a high-pressure sodium light, and what it's doing and when it was last checked. And there's so much information just about the street light itself that if you notice up on the top, this is one of two. You can click on this. This scrolls down. There's about 2 more pages of information of the same length. And then there's a second page which provides even more information about that particular street light. And you can do this with every street light in the city. It's pretty interesting. It's interesting that the city's done this, but then to provide the public access to all the information. And it is anonymous access. They're not providing information about people. There's no face recognition going on here, at least that I could tell from the research that I've done. But it looks like a very interesting and sophisticated system. And so this is sort of the drawing of, here's this smart street light. It's sending information up to the City IQ database. And now they're going to open the database. They have opened the database up to developers. So if you're a developer in San Diego, you could actually request the information, get the information, and then what they're hoping is that developers will build apps that will be applicable and use this data for the advantage of the people in the city. I mean, one of the examples that they used was, could somebody develop an app that uses this information to help people who are blind and help them navigate the city better based on the information that they're collecting? But there are lots of different uses for this thing. And in fact, for me, to go to a city web page, right, a municipal web page, and see a page where it tells you what the metadata is for the structure of the streetlight information, I think that stands out. I never expected to see that on a municipal web page. I don't know if you've ever gone to the web page for your city, but mine doesn't look anything like this, right? When the dump opens, right. So pretty advanced stuff, and I think they're setting the standard here for other cities in the future, and they're really blazing a lot of trails, and it's particularly interesting, and it's very applicable to all the work that we're doing. So we have 2 keynotes today. Matsuo Okasan, who's come to us, he's director of the Riken Center for Computational Sciences. He's leading up a major exascale computing project. He's going to share some insight with us on that. It's really interesting stuff. And then locally, Brian Huntsman, who's been a long-time Connect attendee. He's also on the Linaro board from Qualcomm, and he's going to share some insight with us. So please join me in welcoming Matsuo Okasan.
Hi, good morning. Great day in San Diego. It's a little cloudy, but you know, it's a lot warmer. It's a little cooler than in Tokyo, so or Kobe, where I am. And it's a pleasure for me to be able to speak to you and introduce some of our efforts regarding probably what will be the biggest ARM machine ever, or the biggest supercomputer ever to be created in the world. So before I go on, just tell you who you are. You know, I'm the director of the center of one of the Riken centers with our 15 research centers in Riken. Riken is like, you know, for those who don't know, it's the biggest national lab, research lab in Japan. It's a public lab, so it's like Max Planck in Europe, or maybe like one of the DOE labs in the US. So you know, we've got thousands of people and researchers. But we are one of the 15 centers, research centers in Riken. Other centers do like biology, physics, but we are the center of computation. And what we do, in summary, is we study computing and computing in the high end. So what we say, our slogan is science of computing by computing and for computing. And those of you who have studied US history probably know where the paraphrase came from. But no, our subject matter is computing. We also apply computing to other branches of science, and also we collaborate with other disciplines of science that allows us to accelerate computing. And that's our whole agenda. Okay? And then, so we're a research lab. We are situated, so Riken's headquarters is in actually suburbs of Tokyo, but our center actually is located near Kobe, and we know what Kobe is good for. Right. Yeah. Well, actually, technically, they're not raised in the city of Kobe. City of Kobe is urban, so you don't see any cows. Although we have lots of wild boars roaming around for some reason from the mountains. But we're located here. It's a big building. We're located right in the tip of this landfill, very large landfill. There's another landfill airport, so we're just one station away from the airport. So if you ever come, if you want to visit, let us know, and once we have the new machine, we can take you on a tour. So like I said, the mission of our center is to do research. So we publish papers and do all kind of stuff. We have hundreds of researchers in the area. But the other responsibility we have is to design, build, and operate the flagship supercomputer in Japan. There are many other supercomputers in Japan, and there's a coalition of supercomputing centers, much like, if you know, like Exceed. Actually, UCSD is one of the SDSC, not UCSD. SDSC, for example, is at UCSD is one of the Exceed centers. And just like that, we're one of the what we call HPC centers in Japan. But the difference is we're the flagship center. So we're tier 1. All the other centers are tier 2 in Japan. And being a tier 1 center, we up until very recently, we operated this we built and operated a Scale computer, which was a flagship machine for Japan. And it was the fastest supercomputer in the world by various metrics, not only in the top 500 ranking, which is the most famous, but other rankings too, like the HPCG, you do conjugate gradient, or things like Graph 500, where you do graph analytics. And in fact, and we also won many accolades in applications like the Gordon Bell Prize with the machine. And in fact, K computer was the first machine to retire. Actually, we just retired it. There was a big retirement ceremony end of August. It was the biggest retirement. It retired as incumbent #1 on the graph processing, superseding every other supercomputers or cloud or any other infrastructure, being able to solve the world's largest graph problems, like you do in social networks. So, the machine retired with lots of accolades, coverage by all the TV stations, news. So it became a national event. But why did we retire the machine? Well, to make room for the next one, which we have been planning for many years. The new machine, Fugaku. Fugaku means Mount Fuji. It's the other name for, it's the alternative name for Mount Fuji. For those of you who can read Chinese or Japanese characters, this is Fugaku. So it's a new supercomputer we're building. It's ARM-based, and that's why I'm here. For Intel-based, maybe I don't know. It's ARM-based, but it was built in mind with two large objectives. One is to, of course, to achieve the highest peak in the world. Being able to run these flagship applications, have extreme performance that can only solve problems that can only be solved by computers of this magnitude. But the other is the other objective, which we did not fulfill with K, was to have a very broad base, very broad adoption, and not just the machine itself, but have a very broad proliferation of technology we had developed in the ARM ecosystem. So more users, not just capacity, but more broader sets of applications than just traditional simulation-based applications, data science, artificial intelligence, and so forth, and much broader user base, not just in academia, industry, or or even have these technologies, the derived processors, going to clouds for people to use them in to become the server end of the IoT applications. Okay, so that was the objective. So that's this broad adoption was the other objective. And if you look at now Fuji, it's like that. It has the highest peak in Japan, but also as a standalone mountain has a very, very beautiful broad base. Right? So that's our idealism. So just for the remaining of time, if you're reading email on your smartphones or do stuff like that, but this is one key slide. The rest of the stuff is just explanation of all this. So this ARM, so what we have done is to build a new processor, ARM A64fx or ARM64fx with Fujitsu. And this processor, it's a new processor. It has nothing to do with any of the ARM IP except for the instruction set. It's a brand new processor, and it's a processor that's also is a standard CPU, but also it's been optimized for HPC workloads. So most other processors, including like Xeons and so forth, they have HPC capabilities, but they're not optimized for HPC. I'm sorry, but this is a fact. They can run HPC workloads well, but their main point of optimization is to, let's say, be in the cloud, or run your notebooks, or be in the cloud, and run video streaming. Whereas this, so if your workload is that's a processor you buy, and that's why Intel's selling like billion processors in the market, about 100 million processors in the market. But this processor is entirely HPC optimized. So has extreme high bandwidth compared to standard processors, like again standard CPUs. It has order of magnitude higher memory bandwidth, and memory bandwidth is very important for HPC applications and also for many other apps. It's fairly high flops. It's like 3 teraflops in peak. Has extremely high embedded network bandwidth. Every processor, every chip has 400 gigabits worth of bandwidth going in and out to the interconnect. So think of every node in your cloud having 400G Ethernet. It's the equivalent of that. And then there are various AI supports. So just like GPUs, we have FP16 intake support. But it's still a general purpose CPU. It's not like a GPU. It's not a special purpose accelerator. It's still a very generic CPU. And it doesn't have embedded GPU, just the standard ARM-based cores. ARM-based core, well, runs the ARM version 8.2 instruction set extension with SVE. So the chip can run, it can run Red Hat. When we had the chip for the first time from the fabs, it just booted RHEL out of the box. No modifications, just booted everything right there. And it can run Windows with a little bit of driver support, but it can run Windows. So it can even run Word. So it will probably be the first fastest word processor. And moreover, what would be a processor? The TDP of the processors are kind of rising. Now as you see on the server front, you see processors like 200 watts or even like 220 watts. The recent announcement by like AMD and so forth, or even Intel's some of the high-end offerings are hundreds of watts. But this, I can't disclose the power numbers yet, very soon. But this processor is also very, very power efficient, extremely power efficient. So it's much lower than its competing tiers. So combined with the higher performance and lower power, in terms of power performance, in some of the applications we have seen even order of magnitude faster application performance on a per chip basis compared to, let's say, a Xeon, high-end Xeon. Okay? And then we take that processor, and of course it's been built to scale. Okay? It's for a parallel machine. So there are more than, so we're building a machine that's more than 150,000 of these nodes integrated into a single machine. And so we get something like 150 petabytes per second memory bandwidth. In terms of the number of nodes, it supersedes a little bit more Sequoia, which was a Blue Gene machine in terms of number of nodes. Of course, each processor being much more powerful. And then we get 60 petabits of injection bandwidth aggregate into this interconnect, which is about 10 times all the cloud vendors' internal data center internal traffic aggregated, but it's an order of magnitude higher capability. So that's the amount of interconnect bandwidth we bring onto the system. And then we have petabytes of NVMe storage and up to 10,000 endpoint I/O network. It'll be a little less than that, but with the capability. So in terms of it will not be an exaflop machine per se, but in terms of the capability of when everybody in the HPC community start thinking about what the exascale machine could be. This is the first machine in the world to be achieving the level of performance that's expected at an exascale. But of course, we want the technology to proliferate, like I told you. So, we have been working on this for 10 years, and if I publish this, I think they'll publish the slides so you can look at the details. But in fact, we started working on this machine when K was deployed in 2011. So we've been working on this for almost like 8, 9 years, for a very long time. But we're finally at the very last stage of being able to deploy it. How do we achieve this? Well, it was really a very articulate co-design process involving a lot of the advanced applications that were running on the K as well as on the other supercomputers we had. So we had a whole bunch of, we got the entire application community, HPC application community in Japan involved in doing a co-design with us in our lab, our center, as well as Fujitsu. And so there was a very tight relationship going on. And there's a whole talk about this. I won't go into details today. But basically, this tight collaboration, we picked 9 representative applications from the 9 areas, and 9 areas being what are called priority issues. And there were, of course, application projects in each of the 9 areas, very similar to, if you're familiar with DOE's co-design centers, it's very similar. But we had areas like pharmaceuticals, we had areas like disaster and environment, areas like energy, storage, delivery, also generation, and we had manufacturing, material sciences, manufacturing, and also, but more traditional macroscopic scale manufacturing, like turbines and airplanes and cars and so forth. And then we had some basic science. But all of these applications are of high interest to the society. So we took 9 applications from them, and our objective was to, for these applications, we inquired all the scientists, inquired them like, what's your goal in 5 years, 10 years time, what's your computational requirement, what are the algorithms you're using, how do you stay competitive in the field, and so forth. So everything combined, the goal was set to have the applications run some of the applications run more than 100 times faster than K. On the average, somewhat comparable to that, like 30 times, 40 times, 50 times faster than K. And that was a co-design target. And as I'll tell you later, we have high expectation reaching that. So now you know why we decommissioned K, because the next machine will be 40 to 100 times faster. right? So there's no point in keeping the old machine around anymore. So, so what are the apps? Well, I can give you a few samples. There are lots of a lot of comprehensive examples. Oops. Let me turn off the sound. Yeah. So this is a multi-proteomic simulation. So usually the molecular dynamics simulation is the stuff you see on the right-hand side. You have a single molecule protein, and then you simulate like folding. But in reality, when you want to do, let's say, drug design, you really need to think of the holistic environment. You need to think of like membranes or the inner cell, inside the cell. You need to really calculate all the interactions of the proteins themselves, of course, which are composed of all the atoms. So it turns into this multi-scale, multi-proteomic simulation involving, thousands or even more of that, proteins like that. And so you need to be able to solve this entire system. And you can't do that without having a very large machine. The other would be something like the whole global atmospheric simulation. And, because, at least in Japan, we believe in global warming. Yeah, we do. Yeah. And we think it's an important problem, societal problem. So of course, you need to be able to simulate various scenarios. But for that, you need to be able to simulate, ideally, you need to be able to simulate sub-kilometer scale resolution in your simulation. Otherwise, because of physics, you can't simulate the clouds directly. The clouds, if you have a coarser mesh, like 5 kilometers, then you have to, the clouds are actually sort of emulated, but they're not exact. But being under sub-kilometer allows you to do this type of simulation in real resolution, in reality. And thus you can, the typhoon and all that. But of course, in order to do this, integrate this on the time scales of 50 years, 100 years, you need really big machines. And so we achieved high resolution on K, but in order to do real science, we need to have the power to accelerate by at least 2 orders of magnitude, and we'll achieve that with Fugaku. And like health, we can simulate the heart. Now we can simulate hearts directly. So, cardiovascular illness is one of the biggest killer in the US. But now, in very close future, we'll have capabilities to simulate the entire heart. Of course, in fact, we can do it now. And this allows you to do various what-if analysis. What if you have an anomaly? What if you do surgery? What's the correct, how do you diagnose these things? How do you do the corrective surgery? What's the most effective drugs or any sort of solutions to the problem that's most effective? And this is very exact simulation. You're simulating the cells themselves. You're simulating the blood flow. You're simulating all the electrical pulses. So it's all multi-physics simulation. Again, this is only possible with very large machines. And finally, something that has to do with things like IoT. Well, this is our IoT at macroscopic scale. So we have all these advanced radars like that, like weather, phase array radars. But what we really want to do, and this is also advocated recently in some of the people in the IoT community. For example, one of my old friends, Rich Wolski at Santa Barbara, he's doing lots of IoT stuff. But given his HPC background, he's saying, well, you really need HPC to, once you have the data, you need to simulate things. And what you really do is to have the data, incoming data stream, you have the simulation, you try to couple them together. And that's called data assimilation. So, but to simulate anything like weather, you need to assimilate this kind of assimilation you just saw, in climate. Then you need to assimilate with terabytes of incoming data. And that's not a very trivial problem. But this is like IoT at very, very large scale. So not only you need methods to acquire the data, but you also need ways to utilize the data. And it's not just analytics. To do real advanced stuff, you need to couple that with simulations. Okay, so analytics plus simulation, that's really important. So with that in mind, again, we designed this chip, which there were a lot of stuff we did right with K, so we inherited that. And so again, it's very easy to program, but it's a large machine, but you can basically, all the programs that ran on K runs on this machine without modifications. We retained the bytes per flop ratio. A lot of the new modern designs, they compromised memory bandwidth just to try to get the superficial flops up, but we didn't do that. We retained the bytes per flop. So there's a lot of ease of use and 100 times speed up. However, the new innovations we put into the machine because it's important because, like I said, for proliferation, we really needed this for broad adoption. So one difficulty with K was the fact that the processor was kind of subpar. Well, it was not bad, but compared to, let's say, Intel offerings of the comparable times, the processor was, was not slower, but by and large the same performance. We tested a lot of applications. And that really has no compelling market value, right? Because if you have some processor, and by the way, K was running a Spark. If you're anybody who used Spark stations, I'm sure you're very familiar with what it was. But it was sort of a dying ecosystem. So if you have a processor, a Spark processor, and you have a x86 processor, they perform by and large the same. There's no compelling reason to buy Sparklet. Right. So you need some compelling reason, which is like performance, much higher performance that will get you over the edge and adopt the new infrastructure. Also need to be very green, right? Because data centers these days are very power limited, and being eco-friendly is very important, not just for cost, but for environmental responsibilities. It's not just putting data centers up north where the electricity is cheap. You're still using coal, let's say. Or you may be using carbon neutral power sources, but then some other people are just using using coal to fill the gap. So you really need to build something ecologically friendly as an IT infrastructure itself, not to move your data center somewhere to make it look like it's green. And of course, it has to be part of the global ARM some global software ecosystem. ARM for us was the primary target because ARM ships more than 20 billion chips each year. So this chip will sit at the pinnacle of the overall ARM ecosystem. And of course, we want what we call Society 5.0 in Japan is like it's a new days and age of IT, or like Neoverse in ARM terminology. It's largely the same thing. There's combination of simulation with big data, AI, everything, and security, including blockchain. But these processors need to be the power source of that. So that's a chip we developed, and by the way, it's real. In fact, it's working. It's being mass produced right now in Taiwan, and it's a 7-nanometer chip, and has a high bandwidth memory. It has lots of SerDes for high bandwidth output into the network, and also PCIe and so forth. And so you see the chip here at the center. You see the HBMs right next to it using silicon interposer. And of course it has 48, actually it has 52 cores, ARM cores inside. And I won't go into the details of the architecture. If you're interested, there are several materials that's been published by Fujitsu. There are several talks by me and others. So basically, we have we have what's called CMGs, core memory groups, 4 of them in a chip. They're connected by a cache coherent high bandwidth interconnect. But each of these CMGs have 13 cores, 12 of which are user cores, but all the cores are connected by crossbar. So by being connected by crossbar, there's extremely high bandwidth between the cores. And then there's a level 2 cache, and there's a memory controller. And this, if you're into any of the architecture stuff, this kind of configuration looks very familiar. It doesn't look like a CPU. I mean, the core is a CPU, but it doesn't look like a CPU. In fact, it looks very much like a GPU, right? If you know the processor architectures. In fact, that's exactly what it is. So on one hand, A64fx, one way to look at A64fx is it's a mini-core, again, it's a mini-core ARM CPU with all the intrinsic CPU properties. It runs all the standard codes, it's a mini-core. Single-threaded performance is okay. Very high performance due to higher bandwidth and vectorization, but still it's the CPU core. But architecturally, the underfootings of the processor interconnects and everything, plus the vectorization engine, makes the processor behave also like a GPU. So, so it has a very high data streaming and processing capability. In fact, it has the same memory subsystem as, let's say, Volta, a terabyte per second memory bandwidth. Has the same sort of vector, very wide vector lanes, and it has other memory and streaming memory enhancement features like something like cache localization. Has also being able to synchronize very fast scatter gather support, and it has other performance enhancing features in synchronizing all the cores and so forth. So again, these are features you find in GPUs, and you find them also in this chip. It's not, again, some people ask the question, is there a GPU embedded? No, there's no GPU embedded in the chip, but it's the CPU cores and the aggregate underfootings and the memory subsystem that makes it behave also like a GPU, not just a CPU. Okay, so that's the beauty of the chip. So what's the real performance? Well, so the Himeno benchmark is a CFD, computational fluid dynamics benchmark that's very famous. It's a micro benchmark, so the scores may be a little inflated. But again, it's a benchmark that everybody does, so we did it. And so this is Xeon. By the way, this is a Skylake Platinum, and it's 2-socket, so it's 2 chips. Okay. So a single chip performance is about half of this. And this is the performance of the A64fx CPU. So compared to a dual socket Xeon node, it's about 4 times faster. Okay. And then even compared to like Volta or SXOR, which is a dedicated vector chip, it's faster. It's faster than they are. So on a per socket basis, this chip is about 8 times faster than Xeon on a test CFD workload. And by the way, lower power. So that was a rather synthetic workload. So on the real workload, of course, in some cases, the differences become smaller. So this is WRF. WRF is a very famous weather code in the US. And of course, with real weather code, you have other things like boundary conditions and some physics, which are more compute bound, and compute bound workloads Xeons are actually will do a lot better. But largely, even so, this is again just a dual socket, and this is one CPU, a single socket, and it's about 56% faster, or about 3 times faster on a per socket basis. And of course, this is even on a per socket basis. This CPU is much lower power. So that's the performance. And it's integrated in this way. And under our configuration, there are other configurations, like air-cooled one. We have, because of our scalability, we have this liquid cooling package, about 384 sockets, nodes per rack. You see there are no DIMMs because all the memory is embedded in the chip. And then we interconnect that with the TOFU network, which has 40 gigabytes per second, or almost 100 gigabits per second. But also the latency is in the sub-microsecond, about 0.5 microsecond from node to node, which is 100 times faster than Ethernet, in lower latency than Ethernet. So we connect that. Let me skip over. And then we integrated that in a hierarchical fashion, and we have more than 150K nodes. So right now here, we ended the computer operations. By December, we started installation, and by the first half, we will have the whole machine. So if you put this together, it's about, so we did a lot of NRE, of course, we paid a lot of money for it. But overall, it paid off because, had we built this out of off-the-shelf chips, then it would cost probably 3 times more, machine 3 times bigger, and we use 3 times more electricity. Because we designed this chip from ground up for HPC, because we designed this to be power efficient, because we designed this to be integrated, we got our efficiency. It was a lot of years of work, but we got this. So just to put you in perspective, this compared to, let's say, my iPhone XS Max. Okay, this machine as a whole for HPC workload is about 20 million times faster. So that's like all the cell phones. That's like comparable to all the cell phones shipped in Japan over a year. So think of all the cell phones on a single on a big country being just concentrated into a single group. So that's the magnitude of the scale of this machine. So we did reach 100 times in some of the apps. Some are like 30, some are 40. But we know that we will be reaching 100 times. But again, the software base is generic ARM, plus SVE for vectorization. But everything you expect to run on let's say your x86 cluster, if it can be just recompiled or adjusted a little bit, will run on ARM. And there's been lots of precedence work that have proven that ARM ecosystem is credible. HPC, there are a lot of people who have done this work, say on Thunder X2, and they have shown this to be credible. But now everything will run much faster. And we're porting many applications, HPC apps, and then eventually, but we really want to make this go into the cloud by first providing our services as a back end in alliance with the cloud vendors. That's phase one. But in phase two, we really want, once we get adoption, we really want these chips to go into the clouds directly themselves, to offer HPC services and AI services and data analytics services at high performance, combining cloud to the edge. So it'll be you have the same ARM running on the edge, but you have the highest performing processor of all times running in the cloud and be conjoined. And there are uptakes. On my talk soon, there are uptakes. Already there was announced by NSF that Stony Brook is buying a A64fx based system in the US. It's a Cray system. So now Cray has not made any formal announcement. Fujitsu has not made any formal announcement. We have not made any formal announcement. It's an announcement by NSF. Okay, so bear that in mind. But the announcement says there will be an A64fx based Cray system installed in Stony Brook early next year. Okay. So I'll skip, in the interest of time, I'll skip most of the AI stuff because there will be a talk by my researcher, Alex. Alex, raise your hand. Yeah, the tall guy. Yeah. So Alex will give a talk detailing out our AI plans, especially in training, how we can all be able to utilize the power of A64fx for AI training, very much like GPUs. And so I won't go into the details of that, and since I'm running out of time. But overall, we believe that A64fx will be a credible platform for AI training, because simply each of the chip already has like some of the AI acceleration capabilities, like low precision support, plus very high performance and high bandwidth, but also the interconnects very fast. And when you try to do, nowadays, the real trend is to do scalable training, because the networks are getting much more complicated. In fact, compared to the past, when we saw like the first AlexNet, some of the demands are 6 orders of magnitude higher compared to the early days in the early 2010s. So high performance parallelization is the only way to achieve training in reasonable amount of time, and we believe that the machine is very fit for that. So, but again, if you're interested, I'll leave the details to Alex with respect to what we're doing. And overall, and so we have lots of AI machines now, some of which I have built in Japan. But there's very little public AI infrastructure. The reason why HPC has been successful over many years is because in every country, in the US, in Japan, in Europe, and like China recently, there are public sources of being able to access these large machines. And HPC's success rests on that from the 1960s. Now, with AI, like I said, the real challenge is how to make these complicated networks, deep learning networks, perform and train them, and you really need a big machine to do that. But can you get access to a big machine? And HPC, yes. For simulation workloads, yes. But for AI, there is very little. So we've been building mid-sized systems, and some are very successful, like the ABCI system I built last year with 4,000 volts. And in the US, just about the only public large-scale AI machine is Oak Ridge's Summit, which has actually 27,000 volts. And very, very powerful. There's been lots of great results. But most of the results are dominated by the big players like Google's and Amazon's, who have comparable infrastructures, but they're not open to the public, or they're very expensive for you to buy out of cloud services. So this resource is very important, and comparing that to Oak Ridge, we only had the aggregate of all the machines, only had like 1/4 to 1/5 the performance. But once we launch Fugaku, our capabilities will be higher than Summit. So not only in simulation workloads, but we expect to be able to drive the forefronts of AI, which of course we combine with the edge, to drive the next generation applications. So it's not just about simulation. It's not just about simple analytics. It's really about scaling to tackle the next generation problems that's ever more complicated in this, some people call Neoverse in ARM, well, what we call Society 5.0. And large machines we have built at the very pinnacle of the ARM ecosystem will be one of the resources to do that, but we also expect to see very wide proliferation, including those being embedded directly into the cloud. Okay, with that, I'd like to end my talk, and thank you very much.
Thank you so much. Thank you so much for joining us this morning. We really appreciate you coming here and sharing this with us. Really super interesting stuff. I wish we had time for Q&A, but maybe afterwards. Please join me in welcoming someone that we're very familiar with and has been working with us for quite a while. He's going to share some insight with us. Brian Huntsman from Qualcomm.
Okay, hello everybody. Good to see everybody out here. First off, I would like to give a special thanks to Linaro for inviting me to come up here and give this talk to you today. The ideas for this have kind of been bouncing around in my head for a few years, so it feels good for them to finally be able to get out. And actually, really quick about myself. I've been at Qualcomm Innovation Center for over 10 years now. I've been working primarily in the Linux kernel domain and primarily on smartphones. So what I'm going to be talking to you about today is coming a lot from that perspective. So what do I mean by the upstream bubble, right? So a lot of you may be familiar with the concept of being in a bubble, right? It's the idea of having a constrained environment, having some limitations on it. Those limitations could be really kind of anything in nature. They could be limitations on your interactions, limitations on your perceptions, but the idea is that there's some kind of boundary there, right? And you can take this analogy a little bit further, at least in how I think about it, how it applies to the upstream community, the downstream community, and SoC vendors. A bubble itself can be kind of translucent. You can see beyond it. So people that are inside these domains, they can see kind of things in other domains outside of that, but they generally don't interact with those other domains because they have those kind of boundaries and those limitations. So I wanted to talk a little bit about why is the case, why does this happen with open source projects, downstream product-focused companies, and things like that. So some of you may see this statement and think, all right, yes, absolutely, I agree with that, that makes sense, that's kind of how things are. But some of you may also see this and think, well, wait a minute, I don't like that. That's not really a good thing. It really shouldn't be that way. Kind of based on my experience, I tend to fall in the former camp, and I wanted to spend a bit of time kind of explaining that. Smartphones, just kind of by the nature of the market they're in, the nature of the products, they tend to move very, very fast. I mean, every year you've got a new smartphone device with the latest and greatest hardware coming out in it. And the life cycle for these devices is not really that long in the overall time frame of things, right? People are going to buy a new device, every 2-3 years, or sometimes less if you kind of drop it and crack the screen or something. But the whole idea there is when you're buying a new device, you're buying something that is 1, 2, or sometimes more cases generations beyond what you previously had. There's kind of less need, less opportunity for continuity there, and then that presents kind of some unique challenges. One of the other things that's, to me, really kind of interesting about the smartphone market in particular, which is, I think, brought into some kind of contrast when dealing with the open source community, is just this idea about how the 80-20 rule applies to smartphones. So if you're not familiar with that, the general idea is that smartphones will have a given set of product requirements. Here's the full set of things that you need to support a device. And the 80-20 rule kind of applies to that, in that you can spend roughly about 20% of your effort to get to about 80% of your output, 80% of your goal for those requirements. And for a lot of market segments, that level of functionality may be okay, and even for open source projects like the Linux kernel, that level of functionality may be okay, because once you get beyond that point, you're spending the remaining 80% of your effort to get that extra 20% of output for it. So it's kind of a point of diminishing returns, but on the commercial, on the market side, that's really kind of demanded of products to be able to get to those really high levels of power optimization, of performance, of user experience, and of kind of stability in the products. And that kind of input to the product actually really adds a lot of value to it. It brings a lot of kind of advanced problem solving, advanced techniques that are sometimes kind of problematic when dealing with open source software. So what is the kind of size of the problem I'm talking about? Several years ago, I think it was actually at a Linaro Connect event, there was a speaker that got up and said, SoC vendors have 1 million lines of code downstream in their product trees, and that's kind of a problem. And kind of ever since that point, I've been kind of keeping track of that metric, keeping an eye on it. And so when I went and looked back, roughly 5 years ago, I measured really the number of lines of code that we had to put on top of an upstream kernel to get a product functional. And sure enough, the number for us was over 1 million lines of code. It's been 1.2, 1.4 million lines of code, but it's fairly significant. Over the same kind of 5-year time span, we've been putting a lot of effort into getting our SoC supported upstream, right? So I went back and measured contributions from Coder Forum, which submits support for SoCs. There have been almost 400,000 lines of code submitted in that time frame. And that number doesn't even include contributions from partners such as Linaro or from other kind of community members that would support our architecture. So if you come back to today, you might think 5 years ago, 100,000 lines of code, 400,000 have gone upstream. We should be roughly at 600,000 lines of code, if I can do that math right. But when you look at it today, I measured this, we're still over 1 million lines of code downstream. And that was a really interesting outcome to me. Why is that the case? And to me, it's kind of indicating that the effort there is not translating, at least directly, or at least not at the pace that we might like, into reducing this amount of code that's in our downstream product kernels. So when I started thinking about this, there's kind of several reasons for that. On the hardware side, yes, there is generally a lack of just general device support, things like device drivers and things of that nature. But I think there's also kind of a more fundamental issue at play here. One of the really great things about ARM devices and the ARM ecosystem is that you can take a lot of different components and you can build anything from a very small, very deeply embedded kind of device all the way up to an exascale kind of computer as we saw there. But conversely, that's also one of the maybe not so good things about the ARM ecosystem, because there's an incredible amount of variety and complexity that can come into building these different systems. And fundamentally, one of the challenges here is that there is not a kind of unifying, standardized, required system architecture that comes along with it. There's reference designs, there's specifications, there's best practices, but really at the end of the day, you can build an ARM system that looks very, very different from competitors in its category, and there's still a very good ARM system. So there's a lot of challenges there in being able to support these wide variety of devices with these wide variety of components connected in a wide variety of ways out of a common source base on things. On the software side, there's also a lot of challenges on the upstream side. And smartphones, for me, bring this into, again, really high contrast. I enjoy working in the smartphone market because, at least on the software side, you deal with a very broad and a very divergent range of requirements, right? So when you buy a brand new device, a lot of times you're spending a lot of money on it. You want the best possible performance on it. In some cases, you expect like almost kind of desktop class performance on it. You want very good multimedia, you want very good user experience on it. So there's a lot of expectations just on the performance side. Conversely, these devices are handheld, they're battery powered. When you buy a device, you don't want to you end up recharging the battery every half hour. You want the battery to last 1 day, 2 days, multiple days beyond that. And when these kinds of things, these kind of challenges are presented to software, the techniques that you have to employ to kind of satisfy that wide range of things can be very difficult, fairly complex to do. And there's even further challenges, like on the physical side. These are very small, kind of constrained devices. They've got limitations on the thermal side. There's not a lot of mass there for them to dissipate heat and things like that. You don't want the devices in their hand. All these things kind of come into play. And these aren't just hardware problems. These are problems you have to deal with on the software side. So if you take some of these kind of advanced requirements and you look at how easy is it to support these in upstream projects like the Linux kernel, I tend to find that it's actually fairly difficult. A lot of the current designs in these projects are based around other architectures, and so they're not really kind of designed with these kind of ARM or smartphone kind of requirements in mind. And getting some of these advanced features to be supported there is really kind of an uphill battle at times. There's a lot of work that has to go into it, and I think we're still a far distance away from having those kinds of capabilities supported out of the box. And smartphones have other kind of challenges as well. These days you're seeing every new device is coming out as having multiple cameras in them, versus a few years ago you didn't have that. So the multimedia capabilities are continuing to expand. That places a lot of demands on internal system architecture in terms of things like memory bandwidth and latency for things like system response. If you've been following Qualcomm lately, you may have also heard of this thing called 5G. That's going to be coming fairly soon to a device near you. It's going to be the next generation of cellular networks, but the devices are out there supporting it now, or coming out to market now. And so 5G itself is more than just a simple speed increase. It's going to bring a lot of advanced new capabilities to devices. The speed increases are definitely going to be there, but there's also going to be an overall kind of reduction in transmission latency on the system. So when you bring this into software, there's going to be a lot more challenges in dealing with data flowing through the system. We already have challenges on the 4G side, so it's going to get even further complicated there. So I think on the networking side, there's going to be a lot more challenges in dealing with high throughput kind of data rates in these devices. So I wanted to talk a little bit about specifications. So for the most part, specifications are very good things, right? There's a specific problem, people think about solving it, they create an idea for it, a design for it, they come up with specifications, interfaces for it. That's a good thing. But these can also be dangerous, in my opinion, in certain kinds of scenarios. And the danger to me comes when specifications are treated as standards. And when somebody's making the decision, all right, this specification is going to be the standard, what you're really kind of saying is, this is the best and one and only kind of way of solving that kind of problem. And when you're making that kind of decision, there are kind of implications to doing that. Specifications themselves can be kind of out of sync with product cycles. Products, have to move very frequently and get out to market, and those problems may be solved in very specific ways, and then later on a specification can come out that can address a similar problem. This kind of thing actually happened to Qualcomm when we first moved to 64-bit chips, right? We made our chips, we put our software out there, we were very happy with them. At some point later on, we thought it would be a great idea to get these chips supported in the upstream kernel so that we can start, being better open source citizens. When we went out to do that, we essentially sent our power management code out. People looked at it and said, no thanks, we're not interested in that. And as we kind of got into that, we kind of realized that Qualcomm essentially really didn't get the memo on this one, that the community was, focusing on PSEI as a power management interface. And that there's certainly very good reasons to do that. But for this particular case, the end result of that for us was that our first generation of 64-bit processors really had no path to having power management supported in the upstream community for that. That kind of thing has been addressed kind of going forward, but those kinds of things to me can be kind of challenging when coming from a downstream perspective. Okay, so on the downstream side, we actually have a lot of challenges ourselves as well, right? Because of the market that we're in, timing is fairly critical for us. So if you take the case where somebody decides, I really do want to have an upstream feature, an upstream driver supported in my product, if that particular thing is present when you start using that kernel, great, you're in a pretty good situation. But if you have to do the work to get that kind of thing upstream, then there's going to be problems because the upstream process, at least for the Linux kernel side, is not deterministic at all, right? You can't build a product schedule and say, I know on this date that this feature is going to be in Linus's tree. There's many other things that can come into play. A good kind of example of this is just the Big Little scheduler from ARM. I think there's been many schedules for that to be done and completed, and they were all roughly in the next year time frame. And at the end of the day, ARM spent many, many years working on that, getting it done. It was a good overall outcome. But looking back in the beginning, I'm not sure that they could say definitively it would be a certain functionality at a certain date. And that's kind of hard when you want to go plan things from a product perspective. There's actually a lot of cost concerns on the downstream on the product side. And so I wanted to talk a little bit about the concept of kind of leverage with you. So as engineers, when we have a problem to solve, a typical way of doing that would be take something that is already kind of existing close to what you want, modify it, extend it, add things, remove things, that kind of thing, right? We all kind of do that. Hardware engineers do this too. So this manifests itself kind of within Qualcomm, on the hardware side at least. We end up with a set of chips, SoCs, that are kind of similar in functionality, but all slightly different in some way. And we tend to refer to these kind of as a group or family of chips. So the first generation of these is the one that gets the huge significant effort investment on the hardware and on the software side. And then subsequent revisions of them will be minor tweaks, increase the frequency, take out a hardware block, add a hardware block. But the idea for doing that is you do targeted investment on the hardware side, you manage cost, you manage time, get a product out quicker. The same kind of expectation is there on the software side, right? So when you're going to make these derivative chips, the idea is we're going to go change the software just where we need it and in a very targeted way. We are not going to do a wholesale redesign of the software just to get us back up to the point we are now. But this can have some challenges in other ways. So the hardware blocks themselves are fairly easy to port over between SoC, right? But the software can have different kind of requirements. At the very least, based on timing, you might have to support something in a different kernel version. So already the software has to change a little bit just because the kernel itself is changing. There's another kind of interesting thing I've run into on the downstream side. And it's this concept that upstream is kind of an all or nothing proposition. And when I first ran into this on the downstream side, I was a little taken aback. This is not something I was expecting to see. But I started seeing it repeatedly, so to me this was not an anomaly, not really kind of an exception case. There's a very real kind of perception that this is how things are. So to explain this to you, we have teams internally that kind of are responsible for very focused areas. They've got a hardware area. That's their responsibility. They make it work on the software side. They're responsible for firmware. They're responsible for drivers, libraries, frameworks, middleware, everything. That's their area. They own it. When these kinds of families of chips come in and this leverage story comes in, that hardware block goes over to another device. They've got the expectation that their software, that's going to go over exactly with it as well. The hardware itself internally is not changing, so the software should kind of work as is. And so for the most part, you see that behavior a lot. But when you go to these teams and you say, all right, let's get this piece of hardware supported in the upstream project, they have a different perspective on it. So they view it as a complete separate other thing that has to be supported. The difficulty for them is they pull out their feature description list, basically, and they say, all right, on the downstream product side, I've got this 100 things that I need to do in software to meet all my product requirements. And then they go pull up the upstream side of it, and in a lot of cases, there's something that's existing there that works on their hardware block or something similar for it, but the software story is completely different. They do their investigation, and the functionality tends to be very different. So when they do their line-by-line checklist comparison, the upstream side is missing, a lot of advanced features for the hardware block. They're missing a lot of power management features. They're missing a lot of performance optimizations. They're missing debug capabilities. And that actually becomes a real problem for them because there's no easy way for them to say, all right, we're going to do this work and then we'll be able to use that in a product anytime soon. So when they look at the upstream side, they look at it as we have to maintain our downstream product side and maintain our full investment there. But if we need to go support the upstream side of it as well, now we're doing kind of a parallel, almost kind of duplicate effort to support the same hardware, but with a completely different software base. And if you add that into the challenges of kind of timing, having no real deterministic way to know when some of these features are going to be available, it almost becomes an intractable problem for them. So how do you deal with something like that? How do you get started on that? So a few years ago, one of the engineers on our team and I sat down and asked the question, what would it really kind of take to get one of our SoCs fully supported upstream with this full set of product requirements? And this diagram is not any particular SoC. It's not 100% accurate, but it's a reasonable representation of the kinds of things that we would need to do. So we sketched out a whole bunch of dependencies. This driver needs that driver. These areas are going to have problems. And the end result basically came up with this kind of spaghetti diagram. So just to give you some context for this, this is basically a functional kind of dependency graph where driver A enables functionality needed by driver B. And I color-coded the nodes kind of based on fan out. Darker colors mean higher fan out, means more things are blocking them. Those are kind of the choke points. But then I went back and circled in red. All right, these are areas where we know in the upstream community that this particular feature is not supported, and we'd have to add it. Or we've tried to add it, and the maintainer said, no, we don't like that. Or that functionality really doesn't exist at all. We'd have to create an entirely new way of dealing with things. But essentially, this kind of gave us a way to break down the problem and approach it. So on the positive side, we ended up doing this, right before one of these kind of Connect conferences. And I came in and said, all right, we've got this problem with bus scaling. This is kind of a problem that we've solved downstream. It's unique to us, but maybe others might have some benefit from it. So we talked to some various people at Linaro, and with their help, they kind of engaged with us, worked with us on it. With their help, we were able to kind of get started down the path to something that led towards the interconnect framework. That was several years ago, and then that work is still kind of ongoing, but there was a good outcome there for us. So the other part of the plan that we came up with, we decided, all right, let's not go chase an individual SoC at any given time, because we're never really kind of going to get there if needed. Let's tackle the software requirement pieces and get those enabled in the community, because those are going to be the really difficult ones, and those are going to be the ones where if they're solved later on, we can take individual drivers, and those are much more straightforward to get upstream. So our approach has really been focus on frameworks, focus on software features, and then from there, the rest of the things should hopefully kind of get easier over time. On the downstream side, so companies, at least companies like Qualcomm, behave much differently than open source projects and upstream communities behave, right? So I think one of the challenges for companies that want to engage like that is to have somebody that kind of can understand the external perspective, how they operate, but also understand how your company operates internally. And basically what they should be doing is removing obstacles for participation, removing barriers. To give you an example of this, a few years ago, Linux kernel community started switching over to SPDX identifiers for legal markings, right? So we were paying attention to things, we saw that happening. This seemed like a good thing, and we knew within 1 or 2 product generations, we would be at that point where we'd be using kernel with new product markings on it. So what I did is I actually went out and talked to our lawyers and showed them, hey, look, here's what SPDX identifiers are. Here's what they mean from a legal context. Here's why it's not a big scary thing. They looked at it and said, yeah, that's reasonable. Sounds good. So the next thing I had to do was go back to our internal compliance teams and tell them, not today, but in the near future, you're going to start seeing products showing up with that are marked differently than what we have now. So you don't have to worry about this, but you should be prepared to update your processes, update your tooling. And if you have any questions, by the way, go talk to the lawyers. They're cool with it. And then from there, to continue this on, I had to go back and make actual product plans. I had to go train our engineering teams on how to do this. Pick a point where we're going to start doing this. Tell people what it means, how to do it, show them kind of before and after pictures, and then really get our entire engineering organization up to speed on how to do that. So I think having somebody to do that is really important in the downstream organizations. At least for me, I find cases of this nature kind of coming up almost on a monthly basis. Another really kind of vital thing on the downstream side is really just your overall mindset for open source. As a hiring manager, I will a lot of times take note of people that have kind of gone out of their way to participate in open source projects or open source communities to some extent. Because to me, it demonstrates the ability and willingness to do that kind of thing, which is important for companies like ours who want to operate more in that way. So I think it's a good thing to have there. And if you have those kind of people inside your company, they can help others also learn those kinds of skills. But there's also kind of a counterpoint example there. There are people I found in our company that really don't want anything at all to do with the open source community, or there's people that where I think they would be really good at it and I want them to go do something, ask them about it, and they're really just not interested at all. And that to me is kind of a curious thing, because they work on open source software in their daily job, but they're less interested in engaging with the community. So when I started digging into that a little bit, it came down to a problem of recognition. So companies, at least like Qualcomm, were highly product focused. We recognize and reward things that are kind of product focused as well. And when I first heard that, I was taken aback a little bit because I thought, all right, I value this, our team values this, I know my boss values it as well because he's kind of on me on a repeated basis to do more in this area. But the more and more I thought about it, I recognized that it's a bit broader than that. It's not about one particular group or one particular manager. It's really more about your kind of corporate culture and how they deal with it. For the individual engineers, they don't see recognition from their peers for this kind of activity, and that's kind of that's a really important thing, I think, because to really kind of do well in open source and communities, it needs to be valued and recognized just in a similar way to products as well. And on that front, I think Linaro has been kind of tremendously useful for us. It's one of the things I really appreciate and value about Linaro. Kind of almost universally across the organization, from the engineers to the managers, from the leadership team, they sincerely want to engage with their members, engage with the community, and help their members be better open source citizens. And that is tremendous value. To me, it helps address not just individual items, but also address the kind of mindset issues, the kind of corporate culture problems. It helps essentially kind of bridge the gap between these kind of communities on things. And I'm really appreciative of Linaro for that. So I wanted to share this quote with everybody because I found this as a really kind of a good example of what I'm talking about today. So this came to me kind of unsolicited from one of the engineers within an adjacent group in our company. And to me, it kind of really highlighted how when he first started out, he started out with open source. He had his own kind of preconceptions about what the community would be like, how interacting with them would be. But with some help and some kind of partnership from Linaro, he was able to actually see beyond just his own environment, see how things are different in the upstream side. And it really made a very positive impact on him and the team. And for that, I think it's really good. To me, that was one good solid example. So kind of to that end, I know there's a lot of Qualcomm engineers in the room today, some students as well. And so I wanted to give you a bit of a challenge. So for those of you that have not worked directly with the community yet, not interacted with an open source project, have not been out to a conference like this before, I wanted to encourage you to actually go out and make a connection with somebody outside of your group, outside of your company. Find somebody that works in an area that you work on, or works in an area that you're interested in, and just introduce yourself, ask them a question, ask what's interesting in their area, what's challenging in their area, what's it like working with the community, what's it like working with companies. But if you can take that first step towards getting out of your kind of comfort zone, it'll go a long way towards changing this kind of culture and building this overall better mindset, I think. And when you do those kinds of things, at least in my experience, when engineers kind of come together, when they can talk openly and collaboratively about the kind of common problems that they face, the overall outcomes are much better. I've seen numerous examples where people on the downstream side have discussed something with Linaro, with the community, and the end result for them has been overall much better. And on the upstream side, I've seen a lot of cases where there are things the upstream side wasn't considering. There were new features or capabilities they weren't considering. So I think this kind of interaction is extremely valuable, not just for an individual company, but to help kind of bridge the gap between the communities and help produce better overall results for both downstream focused companies and for the community as a whole. So with that, that's the end of it. Thank you very much. Thank you, John.
All right, Brian, thank you so much. We're running a few minutes late this morning. Sorry for that. So we're going to cut you guys loose to get out of here and get on with the day. And hopefully we'll see everybody at 7 o'clock tonight around the main pool and have a little bit of fun.